Evening, everybody. 5 o'clock Tuesday night, and that means it's time for some Calc 3. So we are getting into what I always call the home stretch. We are moving on to the last module. We're going to be doing some vector calculus. I think we do some really cool stuff in this module. You've already seen some of it with the vector fields, which I think are pretty interesting to work with. So what we're going to do today, so I had you do 3 sections worth of videos for today. But like we talked about on Thursday, 2 of those sections are pretty much the same. One is 2D, one is 3D, but they go hand in hand. So you had 3 sections for videos because I'm only going to cover curl and divergence today explicitly. But as far as the homework goes, the 15.6 homework will actually be due a little bit later. So it's not like you're going to all of a sudden have 3 sections to do for this week. So you'll have plenty of time for that. What I want to do today is I want to talk about the topics that what I want to do today is talk about the topics that were discussed in the videos, and probably we're going to cover them a little bit more conceptually, because I think procedurally, all 3 of these sections aren't bad. I want to point out a few things to you. But procedurally, these really aren't that bad. So let's go ahead and dive into vector fields and talk about those a little bit. As always, if you guys have any questions about the stuff we're covering, just let me know. But basically with vector fields, what happens is it's a function that assigns a vector to each point in the plane or in 3 space. And so the input for a vector field is a position vector. If you remember back to the first half of class, we dealt with position vectors. It turns out we've also seen vector fields before, we just didn't call them that. When we find the gradient of a function, that is a vector field. Okay, so just as a quick reminder, you know, if we have some function f of xy, we'll do something basic for right now. You guys have had some practice doing the gradient. If it's x squared plus y squared, well, then the gradient of f of xy is 2x to y. That is a vector field. All right. Sometimes you'll hear the term also gradient field. So to differentiate between the two, gradient fields are just a specific case of vector fields. And that means that they're the gradient of some function. So all gradient fields are vector fields. Not all vector fields are gradient fields. That's not something we're going to cover a lot today, but as we move on, that's going to be one of the things we discuss, because when we have a gradient field, there's a lot of really cool properties that make some of the calculus we're going to do significantly easier. All right. I just wanted to get to kind of used to that terminology, because we've done gradients. When you guys were finding gradients, you were actually finding vector fields. Just turns out the vector field concept's a little bit more, a little larger than just gradients. So when we have a gradient field, basically what's happening is when we have each gradient at a point, that is our vector field, because really what we have is a vector at each point. So don't worry about the page, but here's a velocity vector field of the Gulf Stream, because what's happening is each vector shows the velocity of the current at that point. All right, so this is a velocity vector field. And this is of, again, the Gulf Stream. And you can see the vectors represent magnitude and direction. So the larger the arrow, the stronger the velocity. The direction that it's going in is the direction of the arrow. Some of these smaller arrows, the current isn't moving as quickly. So the idea behind a vector field, I think, is a little intuitive for us, because we can imagine a current going through a river, and that at certain points in the current, it's going to be stronger, and at certain points, it's going to be not as strong. There'll be places in the river where maybe there's a little bit of a whirlpool, where if you were to drop an object in, it would swirl around in a circle before moving on. So when you think, as you start to conceptually think about vector fields, think about water flowing down a river, because I think that's the most intuitive case for all of us, because we've all seen a river at some point. All right, we're going to talk a little bit of notation here, but this I don't want you to worry too much about. You saw this in the videos. A 2D vector field. A lot of times we'll use this notation. Notice that there's the hat on these guys, f of r, where the components are represented as functions, so like 2x and 2y, where that r is a position vector. So we'll see it that way, or sometimes we'll see it this way. The vector field f is represented by f of xy and g of xy. So here, r is our initial position vector. In the second representation, we're just using the xy and kind of cutting out the middleman of the r there. But basically what we need to take from this is we'll see our vector fields kind of like we have them here on the whiteboard, where we have our two components. We have our I component and our j component in 2D. A 3D vector field is very similar, except we add on the third component, all right? And now each of those components can be functions of 3 variables, because now we're in 3 space. So the main thing I want to point out is when we're dealing with vector fields, the way you're going to recognize it, if it's not explicitly stated in a problem, you'll see the hat on it, indicating that we have a vector field, and its input is either a position vector, denoted as a vector, or an ordered pair for 2 space, or an ordered triple for 3 space. Okay. But yeah, but it'll be pretty obvious when we have a vector field. So a velocity vector field is one example that, again, I think is intuitive. Think of the river, the velocity of the water, and the direction of the water. Another one that we'll deal with a little bit in here is force. So for example, gravity is a force that pulls all masses towards the center of the earth. That is a vector field. Now this is a specific case of a vector field, so we might call it a force field. But as you can imagine, we'd have a bunch of vectors pointing towards the center of the earth if we were to represent it as a vector field. So we want to be able to visualize these vector fields given a formula. Okay. I'm not going to have you draw any vector fields by hand, but you saw in the video how to do that. Basically, you go to each point in the plane and you draw that vector. So if I wanted to draw this vector field, I'm only going to draw a couple vectors because it's going to be messy, but I go to points in the plane. So maybe I go to the point 0, 1. Well, as a vector, the point 0, 1, so x is 0, y is 1, would be the vector 1, 0. So that would be a vector with a magnitude of 1 pointing out this way. Okay. Similarly, if it was 2, 0, point out, be twice as long. Let's just do one more. Maybe we come out here to the point 1, negative 1. Well, that would be the vector negative 1, 1. Okay, so negative in the y direction, positive in the, so that would be the vector negative 1, 1. So we're sloping, we're going backwards in the x direction, but we're going up 1 in the y direction. So it'd be a 45 with a magnitude of rad 2, would look something like that. Okay. So to draw a vector field, what you do is you basically go to points in the plane and then you put those values in for x and y, or x, y, and z. Now, like I said, I'm not going to have you draw any vector fields. I'm certainly not going to have you try and draw any 3D vector fields. But it is a good exercise to draw a couple basic vector fields just to start to get used to that relationship. Now, let's actually see what this looks like. Now, to do a vector field in Calc-Plot3D, you can add a vector field. Oops, not a vector, excuse me. Add a vector field. We're going to come back to this. There's going to be a lot of cool things we can do. And we're just going to do this basic one, y, comma, x. And I'll show you a couple different things that are pretty cool that this can do. Now, here's our vector field. Well, notice the z component, the k component, excuse me, the third component is 0, which is why it's only in the xy plane. So let's restrict our view to 2D. So that's what this thing looks like in 2D. If you like the multicolor, you can turn that off. And so here is what our vector field looks like. Now, we only drew a couple vectors. We drew this purple one here, and this, well, here's the one at 1, and we drew the one at 2, which is twice the length. And then we drew the one at 1, negative 1, which is this upward diagonal. But this is a vector field created by this here. All right. And again, the Calc 3D plotter can do it. Like I said, I'm not going to have you draw them by hand, but I do want you to get used to relating the equation of the vector field to the view of the vector field. Now, as you can imagine, there's too many options, vector fields, for us to go through them all, but that's why we have the Calc 3D plotter. There's other vector field plotters on the web. If you Google vector field plotter, you'll find others. So if you find one you like better, feel free to use it. I'll show you a couple of cool things that this one can do. Now, here's something that's pretty cool about vector fields. So what we are often concerned about is the path an object will travel once it enters a vector field. So going back to our river example, if we drop an object in the river, what kind of path is it going to follow, assuming it doesn't sink? Well, what kind of path it follows depends on where it's dropped. And so what we do is we use the information in the vector field to determine a path. So this will depend on where it starts, what the direction of the vectors are, and what the magnitude is. Once we do this, what that creates, once you pick a starting point, so maybe we start right here and it kind of follows along our vector field, it creates what are called flow lines. Check out right here, flow line solution curve. So if we pick a point, that's, say I drop an object right here into our vector field, that line represents the path that it would take. Now, as we just said, depending on the starting point, it changes our path through the vector field, right? If we start over here, we're going to end up there. If we go up a little higher, we end up here. This is what's called a flow line. Now, this should sound a little familiar for anybody who's done a little bit of work with differential equations. So with differential equations, what you do is you create a slope field And then once you have an initial condition, which would be this point here, you have a path through your slope field. This is the exact same idea. We create a vector field. We have an initial condition, which is where we decide to start our path. And then the flow line is the solution to that vector field and initial condition. The flow of a vector field is the collection of all the flow lines. All right. Now, we're not going to worry about the flow. Obviously, there's a whole bunch of different options. And we're not going to be finding flow lines in here. I just want you to be familiar with what they are, because we are going to be interested in paths that things take as they go through a vector field. So back to our Gulf Stream example, this was our vector field, our velocity vector field. Here is our flow. So you can see the family of flow lines. If we go back again, you can kind of see how they're related. Where if we were going to drop an object into the Gulf Stream, we know what path it would take. So that's what the flow is and the flow lines. Now, the reason that these were so intertwined, the idea of velocity of a vector field and slope field, is because if we had a velocity vector field, so, and we let t be in seconds, we're just going to do a 2D field for this example. Well, then the derivative of our position vector, the derivative of our position vector, which is velocity, is the vector field, okay? So if we say r of t equals x of t and y of t, and our vector field is given by f of xy, g of xy, then what we have is that f of x of t, y of t, g of x of t, y of t equals x prime of t, y prime of t. So the flow is the general solution to a system of the above system of differential equations. Now, this is not something we're going to be solving in here. Not all of you have done differential equations, and that's totally fine. I just want to make this connection explicit for you guys that to find the flow of a velocity of a vector field is solving the system of differential equations, and that's why doing this flow line seems so similar for those of you who have done differential equations, because that's actually what you're doing. So what you would do is set up a system of differential equations, an initial condition, which would be like our blue point, and then the solution would be the flow line. In differential equations, we call this the solution to our system of differential equations. Again, not something you need to be able to solve for this class. So I don't want to freak you out that I'm talking about differential equations, but I want to make that connection because almost everybody in here, if you haven't had differential equations yet, you will. So I just want you to see that relationship. What I want you guys to take from this is, well, we have a velocity vector field, or in general, a vector field. Depending on where our object starts in the vector field, we'll have a particular path. That's all we need to take from this. All right, so we're going to look at some different kinds of vector fields. So we have things called radial, and you're not going to need to memorize these definitions, but radial vector fields, are vector fields where along some radius, all our vectors are the same length, and they either point away from the origin or towards the origin. And you can kind of see if I draw a circle, all those vectors on a circle would have have about the same length. there's also rotational vector fields, and these are ones that tend to go in a circle. So if I dropped an object right here, you can see we'd follow this path, and we'd end up where we started, hence rotational. And here's what those vector fields will look like as functions. Not that you need to memorize those terms. I just want you to see a few different vector fields. These radial and rotational vector fields, we have them in 3D as well. So here's a couple radial vector fields. Here, everything is going away from the origin. Here, everything is going towards the origin. So this mimics a gravitational vector field because everything is being pulled towards one point. As you guys go through the lessons, the homework, and a few of the worksheet problems, you'll get very used to all the different kind of vector fields. I'm just presenting just a couple of the more basic cases. Yeah, gravitational one would actually get stronger. I can't remember if these are all the same length or if they get shorter because of the angle. But yes, a gravitational vector field would get stronger as it goes towards the center. And these look like they get shorter. They might be staying the same length because this is at an angle. And unfortunately, I can't rotate this one because it's a static image. Okay, one last thing I want to mention on vector field. Oh, here's a rotational one in 3D. It's so convoluted you can't really see anything. But let's see. Let's change this to a radial one. So there's our radial vector field. This one has, I don't think this equation's quite right because it's got some z component there. Let's see. Now you can kind of start to see how this radial vector field looks. So again, guys, use the 3D plotter so you can play around with these, and you'll start to get used to what these will look like as you go on. Probably make it a little more interesting for you. So those are just the introduction to them. Now, we did talk about this, and I'm going to bring it up one more time. If we find the gradient of a function, that creates a vector field made up of the gradients. Easy example is x squared plus y squared. Because, sorry, that came out of order, because the gradient is 2x, 2y, which is a vector field. If that happens, if our vector field is a gradient field, we call the function that produced it a potential function. All right. Not a huge deal for today, but it will be very important when we start looking at line integrals. So I just want to get that term out there. A potential function is a function whose vector field is a gradient field. So here's everything plotted together. Here's our gradient field plotted with some level curves. And you can see on a particular level curve, all the gradients are the same length. So we're starting to tie some stuff that we did back in module 3 with some stuff we're doing now, particularly the gradient. Questions at this point? Vector fields, I think you'll get the hang of them pretty quick because really all that's going on is we're getting a vector at each particular point, and that creates the whole vector field. The biggest thing I think when you're seeing them for the first time is just to get the connection between the vector field itself and what it looks like graphically. And Depending on how complicated this can be really messy, as you can imagine. And I'm not expecting you to draw them. I just want you to be able to start to get that relationship down, and you'll be able to use the plotter to plot any really complex ones. Okay, then next thing is to talk about the curl and the divergence. Just a sec. Now, here's something I'll tell you before I even get into this section. You saw the videos on these. First off, computationally, these aren't bad at all. In fact, divergence may be one of the easiest things computationally in this class, if you're comfortable with your partial derivatives. The curl, a little bit trickier, but as long as you have the formula, which you're allowed the note card on the exam, you should be able to calculate the curl. So what I'm going to spend more time is on in this section is just talking about them a little more conceptually. I'll also mention what this Dell is. It's more of an operator. And then we'll talk about the formulas. And then when you guys break into groups, you'll get to calculate a couple. And I think you're going to find divergence really easy and curl not too bad. Okay, so let's talk about divergence first. So divergence is used to measure at any point its tendency to be a source or a sink. Now, what a source is pulling things in towards a point, and a sink is something that's going outward. So it basically represents the volume density of the outward flux of a vector field. What we're going to do, so the divergence is calculated at a single point. Later on, we'll talk about, later on this semester, not today, not later on today, we'll talk about using the divergence in order to look at the total flux of a surface. But just to give you an idea of what's happening with divergence, imagine air as it's heated, it expands in all directions. So that would be a source. So basically what's happening is the velocity field points outward from the region. Now, if the air was being cooled, then it's going to contract, and we would have what is called a sink. So when we're looking at divergence is the extent to which it behaves like a source or a sink. Positive would be a source, negative would be a sink as far as calculating divergence. And it's a measure of outgoingness. So at any given point, how much are things being radiated away versus how much are they being sucked in? So, the expansion of a fluid is captured by the divergence. Divergence is a scalar. So again, at any given point, it's the measure of how much it's going in or going away. So let's do our radial vector field here. So let's bring our vector field back. We'll go back to the 2D. And we're going to add in the divergence at a point. So here's what's happening. I've got this point, and these green arrows are the measure of the divergence because they're looking at how much at the region around the point, which is the red, things are going away or towards the point. And you can see some of these areas on the opposite side actually kind of go through it. So that would be a bit of a sink there. Whereas these ones that are on the radius and pushing away are representative of a source. Now, as I move this point around, we can see the divergence decreases and the divergence increases. Let's reset that. Okay. And as we get further away, these get larger. Well, that makes sense because the magnitude of our vectors get larger. So that's what's going on with divergence. Basically, it's saying at any given point, to what extent is there more going in towards the point, which would be these arrows here, versus going out. Let's make our vector field a little bit more interesting. And I just need to reset it. There we go. So again, we can see, okay, how much is going in versus how much is going out. Now, I know you're probably wondering, so this actually does calculate the divergence for us. And the reason the divergence is coming up as 0, we'll see that here in a second when we look at the calculation. Again, these are just some examples of just kind of getting that idea of, okay, this would be a source, everything's pointing away. A sink, everything is pointing towards. Calculating the divergence is actually very easy because all we do is we look at the partials of our vector field. So for a 2D vector field, we take the I component with respect to X plus the J component with respect to Y. Again, the divergence is a scalar, so we just add them together and we just get a single number. Now for our vector field here, we can actually see why it is that we're getting a divergence of 0 down here, because the derivative of Y, so the derivative with respect to X of negative Y, well, that equals 0 because it's a constant. The derivative with respect to Y of the second component, X squared, equals 0. So our divergence is 0 plus 0 or 0 for all points. Now, obviously, that's not going to always happen, but I just wanted to show you why we're getting that 0 there. It's going to depend, obviously, on your vector field. And again, just because our divergence is 0 doesn't mean that we don't have things going in and outwards from the point. What it means is they cancel each other out. There's as much going in as there is coming out, which is why we're getting a divergence of 0. The 3D divergence, all we do is add on that third component. Again, very easy to calculate. You know, just a mental note or in your notes, remember, divergence, whether it's 2D or 3D, is a scalar. And it is pretty straightforward. You basically take the first component with respect to X plus the second component with respect to Y, or first component with respect to X, second component with respect to Y, third component with respect to Z. So it is very, very straightforward. You guys I'll have you calculate a couple, in one or two in your group, but I think calculating divergence is, again, one of the more straightforward things we have in here. Questions about divergence?
Hey, I was wondering if you could put the divergence little dot in the very middle of the XY plane, because I kind of want to see them all go toward the middle. Oh, they didn't. Okay, all right. I thought they'd go straight to the middle. That's all I was wondering.
Oh yeah. So
Really curious about that since you started doing it.
yeah. Notice so remember two things I want to mention about what's happening here. The reason that they're going the direction they're going, notice how they do mimic our vector field, right? Our vector field kind of goes around like this. Well, these kind of go around as well. The other thing I want to point out about the way that this is doing divergence, what it's doing is it's finding the vectors along the red radius, okay? Now, when we calculate divergence, we do it at a specific point. So when we calculate divergence, we're calculating it at that black point in the middle. What we're looking at graphically, this graphical representation is basically an estimate of the divergence, because what it's doing is it's finding vectors that are around that point. They're all within this circle, which you can see is a circle of a radius about a quarter. So these are kind of estimates of what the divergence is at this single point. So what we would expect to see are arrows that go along with our vector field, but maybe aren't exactly what's happening at the point, because what they are vectors that are around the point. Other questions about vector fields? Excuse me, divergence. Again, this is going to be something you guys can play with. It's actually a pretty cool program that we actually get to move a point around and see what the vectors are doing. All right, let's talk about the curl. So curl measures rotation of a vector field at any given point. So what does that mean? What happens is we obviously have a rotation going on here in our vector field, but there's also a rotation going on at a potential rotation. Not necessarily there is one. There's a potential rotation going on at each individual point. And the curl represents the magnitude and direction of that rotation. So I'm going to give you a couple ways of thinking about the curl. So imagine having a whirlpool, and if you shrink it down smaller and smaller while keeping the same force, there's going to be a lot of power in a small area. So if you're rotating in a really small area with the same amount of force, you'll have a large curl. As you widen the whirlpool, still keeping the force constant, it shrinks the curl. Here's another way to think about curl. You can think of it as the amount of force pushing, twisting, or turning when the path is shrunken down to a single point. So imagine putting a small flat surface in water. For example, an oar, or OAR, so the oar of a boat if you're paddling a boat. If you put that oar in the water, if that oar twists, then the force is stronger on one side than the other. Then there is a curl going right down the middle of that oar at the insertion point. That's what the curl would do. It would cause that paddle to rotate. The harder the twist, the larger the curl. Now, if there's no twist at that point, the curl is 0. Now, when the curl is 0 overall for an entire vector field, then we have what's called a conservative vector field. And that's going to be our favorite case, because that's where we're going to have a potential function. Now, we're not going to spend a lot of time on that today. We're just getting used to these ideas. But when the curl is 0 for an entire vector field, not just at a point, but for an entire vector field, we have a conservative vector field. And when we have a conservative vector field, it's a gradient field, and there is a potential function. So All those ideas are tied together. We're going to explore this idea more in subsequent classes, but I'm just bringing it up today since we're talking about the curl. Now we have a 2D curl. So a 2D curl is a scalar. Now this one we want to be a little bit careful on because things got reversed on us here. So now it's the second component with respect to x minus the first component with respect to y. And the order matters because we'll get a positive or negative. So if we're using this vector field here, again, this vector field that I have plotted, this would be the vector field negative y comma x squared. So if we wanted to calculate the curl, we would do df2, which is the second component, dx, which is the derivative of x squared with respect to x, so 2x, and the derivative of f1 with respect to y would be negative 1. So our curl of f would be 2x minus 1. Notice it's not equal to 0, so this is not a conservative vector field, which is fine. But this is what our curl would be. And now we can evaluate that curl at any given point by plugging in the point in the xy plane. Now, there's two things going on with the curl. There's going to be a magnitude and direction. So let's calculate the curl at the point 1, 1, let's say. So if we wanted to get the curl at the point 1, 1, well, our curl would equal 2 times 1 minus 1 or 1. So this does two things. This gives us the magnitude, but it does also give us the direction because it's positive. If the curl is negative, it'll be the opposite direction. So let's get the curl on here so you can kind of see what's going on there. This will also do curl at a point. Notice that it's rotating, and it's rotating counterclockwise. Now, we can tell by our curl that if x is negative, we'll get a negative curl. So let's move this over to a place where x is negative. Look at what happened. We're rotating the opposite direction. So positive curl goes counterclockwise, negative curl goes clockwise. So we do have a direction associated with this. It's just we only have two directions in 2D, clockwise or counterclockwise. Also, notice the rate. The rate's much lower here, telling us that our curl is much smaller here as well. If we bring it over here, we got a larger curl. You can see our curl being calculated up here. Bring it back over here again, got a really small curl. All right, and it's going really slow. If we start to move a little bit away, our curl gets bigger and it goes a little faster. Further we get in the negative x direction, the bigger our curl gets. Well, that makes sense based off of our curl right here. So
why is the curl, oh, excuse me.
Yeah, go ahead.
Why is the curl not the most toward the center? Because like if I think about curl, looks like the center is where it's going to be curling the most. That makes sense. Does it make sense? How I'm being like intuitively, it just looks like the middle of it. Yeah, exactly. It's like tighter like that. But like, why is it when it's super far away and there's not really much curve to the slope field that there's more curl?
Because it's not based as much on curve as it is on magnitude.
Okay.
Because when we got out to these outer parts, we had more magnitude in our vector field. That's causing it to spin faster. Whereas when we have the smaller magnitude, it's still rotating, but there's not as much force behind it, so it's rotating slower.
So it's not about the speed that it changes direction. It's not about how quickly it changes direction. It's just about like the general magnitude.
It's a little bit of both. But yes, the magnitude is going to be what, so the direction of the arrow is going to give us the direction that we're spinning. The magnitude of the vector field is going to give us the rate that we're spinning at.
Okay, that makes sense. Thank you.
Yeah, no, it's a good question. Other questions while we have this up. And guys, like I said, this is something you guys can play around with. You have access to the 3D plotter. So play with it. It's how you'll get used to this stuff. It does some really cool things. All right. I'm going to stop that from spinning because it can be a little distracting. We'll go back to a path. There's a cool path. All right. Now, conceptually, there's nothing different going on with the curl in 3D. All we have is an extra component. But because we have more possibilities for direction, the curl is no longer represented by a scalar, it's represented by a vector. Okay. To do the 3D vector, you saw this in the online lesson. It's not that bad. It's basically just doing the determinant of a 3x3 matrix, or guys, you can just use this formula, right? You can have that on your note card, and that's totally fine. I'm not going to have you do any 3D curls on the proctored exam anyways. I'd just have you do a 2D curl. But a 3D curl is something you'll do, in the homework, possibly a take-home problem. So we do need to be familiar with it. And let's see if we let's get a good 3D vector on here. If I can, so we can start to at least see what it looks like. So there's a 3D vector field. Still got that rotational aspect. So I want to exaggerate that a little bit. Okay. So here's a 3D vector field. And just like we did before, you can put on I think you can put on the curl. Yes. But to put on the curl, this is for 2D. To put on the curl, we can go up here. And this will allow us to move points around in the XY plane. Okay. Right now we're on curl, but you can do flow line, right? There's a flow line based off of that point. To move the point, you have to use this little pad over here. So you can get your flow lines. The reason we're not getting as much in the Z direction is because of right here, the number of vectors on the Z axis. So let's put in a few more so you can get a better, gets a little messy. Let's just do 2. I don't want to get it too messy and take away from what we're doing. Now, let's go back to what we had. So there's one thing I want you to see though. So there's our path. You can do divergence. So you want to switch over to divergence, move the point around again. You can kind of see to what degree is it a source or a sink. Still calculated up at the top. Again, I happen to pick a vector field that has a 0 divergence, so a little boring, but what that means, again, is all those points, the in and out, are canceling out. You can see it better in the 2D. These guys are going in towards our point. These guys are going away from. But I wanted you to see the curl because there's one thing I want to show you on the curl. This is the vector of the curl. All right. So, the video talked about that right-hand rule. There's the vector. And then once you do your right-hand rule, you'll go in the direction, your hands will curl in the direction of the rotation. So we can see that guy rotating there. All right. So once again, we can move this around and it'll show us any of those points, what kind of rotation, what kind of curl we have going on. And guys, you can use this to check your calculations. That's going to be a pretty small curl there. You guys can use this to check your calculations because you can put in your vector field right here, and then you can have it calculate the curl at the point. You just have to put this on whichever point you're looking at. So for instance, 1, 0, that'll give me my curl there. It's 2K. Again, remember I was telling you before, when you do the divergence, it's always a scalar. The 2D curl is a scalar. Positive and negative tell us the direction. The 3D curl is a vector. The vector gives us the direction. The magnitude of that vector is the magnitude of the curl.
I have another question.
Yeah.
So when you do the cross product,
Mm-hmm.
so like let's take the first term of the I vector on the right. Yeah, in the center, I guess it'd be. When you multiply them, instead of having to take the partial of x and then multiply it by f3, you can literally just take the partial of f3 with respect to y.
Yes.
Oh, that's really cool. So it just multiplies together like that.
Yep.
So you wait until after the fact to actually do the derivatives instead of doing them ahead of time and then crossing them.
Yes, because what's going on is, you know, from a determinant of a matrix standpoint, you know, so we're doing the I component, so we kind of cancel those out, and then we do our 2 by 2 matrix, which is that fish thing I was talking about.
Yep.
Right there.
But when
and
you
that's what gives
multiply
us
the
this
partial with respect to y, by f3, it multiplies into the partial of f3 with respect to y.
Yes.
So it saves a whole step of having to do the partials and then multiply them, kind of messy.
Yeah, I think this is a cleaner way to do it.
Yeah. Okay. I didn't know that. That's how it worked. That's awesome. Thank you.
No problem. That's it's part of what we're getting used to. Last thing I'll mention, just because it's in the title, is that Dell operator and what it is. So you can think of the Dell. They were calling this guy Dell. You know, we saw this in front of our gradient. What the Dell does is it basically means we're doing the partials with respect to each variable. So treating it as an operator, one way of writing the divergence is thinking of it as the dot product between del and f, because then we're doing the partial with respect to f of f1, partial with respect to y of f2. And this is this is similar to what Cooper was talking about. We can do it in 3 space. And I don't have it on the slide, but it can be done for curl as well in 3 space. So the curl of f is the del operator crossed with f. So it's just a shorthand notation. And that's all it really is telling us, is to take the partial with respect to each variable. X is in the first component, y in the second, z in the third. So I just wanted to mention that just because it's in the title of this section, but you're already doing it when you're calculating divergence or curl. Okay. Questions at this point? All right, I'm going to break you guys up into groups so that you can try some of these. And guys, all of these are pretty short. They're from the 15.1 and 15.2 worksheet. So there's going to be the problems. And just remember what it is you're being asked to do. Okay, you've got the formulas. So now we're just going to practice using them. Okay, so let's see. Oh. All right, so I just want you to try these problems from the worksheets. You can grab those out of more. Guys, there's 3 problems I'm asking you to do. they're all pretty short. So I think we're going to have enough time to get through these, and these are going to be the ones that you can post. But I want you to have tried them, before you get a chance to try them before you leave. If you have questions, feel free to call me in your room, and we'll get through it. All right. So let's see. You should have the room should be open now, and should be able to get in there.